CHK, so that if you feel that Friday is not your favorite slot, please make your votes in this paragraph, and please make your attendance here. I will pass this paragraph from here. Okay. So today we are honored to have Elton Zhong to present about the supercomputing development in CHK, and without further ado, let's Elton Zhong kickstart the meetup.
Right. So thanks all of you attending today's seminar. So I'm Elton. So I'm one of the team members of ASC 15 of the CHK team. So today, I'm really happy to have Open Innovation Lab to invite me to give this talk. So today we will cover students and supercomputing. Okay, so in case someone don't know what is supercomputing, so I just give a photo here. So this is the IBM Blue Gene. So which this computer somehow did beat the one of the famous chess player in the outside. So this is how supercomputer looks like. So it basically is quite lots of computers interconnected together. So if you search Wikipedia, you can see. So supercomputer basically means a computer with high level of computational capacity compared with general purpose computer. But so this definition can somehow be quite confusing, because sometimes when you say a computer, you think about only one computer. So let's not use the word a computer, but let's instead say a cluster of computers. Right. So a cluster, what is a cluster? So a cluster is computers connected together. So it's basically a group of computers, and then the usage is to accelerate computation. So as mentioned, a supercomputer has much higher computational power than a general purpose computer, like the desktop in your home, or your laptop, or your tablet. So supercomputer provides much higher computational power. And why there exist clusters? So it's basically because of cost effectiveness. So imagine if you have some really high-end machines, maybe they have more than 8 cores, like 12 cores, or even more, but they can be much more costly than two less core computers. Like an example is that maybe 2 8-core CPUs can be cheaper than one 12-core CPU. So that's why there exist clusters, which provides a way to have lower cost but to achieve higher performance. Right. So after seeing that IBM Blue Gene, which you see there are lots of computers interconnected together, you may wonder, so what's students' role in supercomputing? Right. So basically, students in supercomputing, you can serve as the system administrator of the clusters, or you can also participate in some supercomputing competitions. Okay, so maybe some of you saw on the poster that there's something called the SIGSC. So what's the SIGSC? It is the special interest group in supercomputing in CHK. So it is formed by the CSE and the physics department in this year, and then we are currently having ongoing training on Tuesday and Thursday. But due to some resources formation, so it's only currently available to CSE and physics students only. Yeah. So inside the SIGSC, we don't have that IBM Blue Gene, but we do have a cluster of computers which is formed by some Dell precision workstations. So, but they are still much more powerful than the computer inside home or your laptop. So they got 2 Intel Xeon CPUs, which each of the CPU got 8 cores and 16 threads. So on each of the workstation, we got 16 cores and 32 threads. And then we got 64 gigs of RAM, so it's much higher than the general purpose computers. So we got like more than 100 gigs of SSD installed on our workstation, and also we got some NVIDIA GPUs, which is the Quadro K600, but this is not that powerful. We just use it to train ourselves on CUDA programming skills, which I will also cover about GPUs later. And then we also got some InfiniBand connector, so which I will also introduce later. And then we also got CO5, which is actually something different from GPUs, but it is also connected just as GPUs, and they also somehow look like GPUs, which I will also cover. And lastly, so we install CentOS on our workstations, which could be familiar to some of you guys if you have installed some Linux distros on your computer as your main OS. Okay. So the first part, let me first cover our student system admin of customers. Right, so what's the role of system admin in the special interest group or in the ASC competition, which I will cover? Basically, it's to make sure your cluster or your training computers will not be down for an extended period of time, because you would like your members to exercise their programming skills and then test whether their programs are working or not, rather than always claiming that, oh, why the cluster is down and I cannot connect to it, right? And then the second thing is we would like to do custom maintenance and to do software updates as sysadmin in the cluster. And then we also need to identify and fix some system issues. Okay. So focus of sysadmin in the SIG-SC or the ASC, basically there are quite some parts like the OS, operating system, interconnection, storage, coprocessors, and how you combine all of the four above, and how to provide a being stable system, and then some tuning or some compilation and runtime software also being installed on the same machine. Well, sorry for having a Chinese topic here. Basically, it's the hospital authority. Maybe you have knew on the news that before in October, the IT department of the hospital authority, they accidentally upgrade all the Internet Explorers to IE 11 or 10. That made all the computers inside the hospital not being able to connect to the internal systems. So that really caused quite some problems. So you really don't want to see something like this on your cluster that made your users not being able to run their software. So how to play safe on cluster is that you select some commercially supported or HPC-specific OS, like the Red Hat Enterprise Linux, or Core Rail, or CentOS, or Ubuntu, SUSE, or ROS. I know some people, maybe some people heard of some other OS like Arch Linux or some other not really that mainstream OS, but basically we do not use those OS in high-performance computing because they could cause problems. And sometimes this OS, provides some kinds of benefits to you, but it's not that mainstream in HPC, I would say. And then kernel is not a place to experiment with in HPC, because in HPC we like to provide a really stable environment for people to run your software. So we don't play anything or change the code on the kernel usually, unless you are really powerful enough to ensure that if you change the line, any lines of code in the kernel, and then it won't crash the system. And then the last thing is that we usually install stable releases of software, because some bleeding edge software could cause problems. Maybe they improve some features, but sometimes they also cause some regressions, or they introduce new bugs in the code. So first, the first area is the operating system, or the OS. So the perspective is the server OS. So we don't care whether you use Genome 2, Genome 3. We don't care about the GUI. And then the main concern is whether the OS is easy to manage and whether it is stable. So kernel version is somehow an indicator, because in HPC we really somehow concern the kernel version, but not that much, I would say. So some performance enhancement has been added to related to HPC in kernel 3, but then right now we got kernel 4.0, but that's not really something that we would like to chase on. So we don't need to chase the latest version of kernel here. And then why we don't want to chase the kernel version is that sometimes if the hardware vendor does not support the latest kernel versions, then it could cause a problem on your system. So we like to have a balance between the usability of the kernel and also the kind of support of that kernel in your system. Right. So in case someone is only a newbie to Linux, I would like to introduce something called distro. So in distro, in the Linux distro world, there are quite a lot of distros, and then mainly there are two types of distros in the enterprise world. So the first one is the Debian base, and then the second one is Red Hat base. So the Debian base is those like Debian or Ubuntu, etc. Like the maybe in Ubuntu you got a lot of other flavors, so they're all inside the Debian-based world. But in the other hand, you also got the Red Hat-based world. So you got Rail, which is the Red Hat Enterprise Linux, and then you got CentOS, which is the open source alternative to Rail, and then you've also got ROX and Scientific Linux. So they're all inside the Red Hat-based world, which I could say that people seldom mix these two kind of distros inside the same cluster. So either they install Ubuntu or either they install Rail. So they seldom mix these two kind of distros together in a single cluster. So so what's interesting in distro is that some have quite aggressive release approach. Also, some people may wonder why I didn't cover Fedora, or some people may think, well, why you didn't cover any other leading edge Linux distros. That's because you can see that some got quite aggressive release approach, like Fedora. In every 6 months they got a new release out, but that's not something that is interesting in the HPC world. Because imagine if you use Fedora, then every 6 months you need to update the OS on all your machines. So that's not something interesting to the system admin and also the user. And then at the same time, some got much more conservative or we will use the word enterprise release approach. Just like CentOS, you can see that basically each major version of CentOS is being supported for at least a few years. Some also got even longer release approach. Like Ubuntu, you got some long-term support versions. So that's what we are mentioning about enterprise release. So this is something, just an example, that tells you different distros. There are different approach to manage them. So you can see in Debian base and Red Hat base world. So just an example, when you update a package, you need to type in different commands. So that's one of the reasons why you don't want to mix two of them into the same cluster. So that's just about OS, and then let's cover interconnection. So you may wonder how clusters are being interconnected. So at your home, you may have been subscribed to a fiber connection. Maybe you get 1 gigabit per second or 100 megabit per second connection as the internet connection at your home. So how are clusters interconnected? I mean, not to the internet, but how the internal connection works. So on-board LAN adapter is one of the choice, but let's provide mostly 100 megabit or 1 gigabit per second of speed. That could be acceptable for some mainstream users, but in the HPC world that is not quite fast. And also on-board LAN connector, for on-board LAN connector, the latency is quite high, and then also the cost is low, but you're going to lose quite some performance because it is cheap, but you only got 1 gigabit. So, but in HPC world, we're talking about several, at least like more than 10 gigabits per second. So on-board LAN connector is a low cost, but losing performance choice. So what can we choose? So just as mentioned in the machine spec, so we got InfiniBand, and on the other hand, the high-speed Ethernet choice, which is not available on our cluster, but is becoming more and more familiar today. So what is InfiniBand? You can see on the screen that you got a specific PCIe adapter card, and you also got specific cables. If you can see clearly here, it does not look like some RJ45 cables inside your home. Instead, it is actually having a chip inside, and the size of the adapter is also not the same as your RJ45 cable using as the Ethernet cable at your home. So they're quite costly actually. So this part alone costs you several $1,000s, and then one cable would cost you like $1,000. So playing in the HPC world is not something that is very affordable, maybe you can say. So it's quite resource intensive actually. But what's the advantages of using InfiniBand? So it enables you to ditch TCP/IP, because in InfiniBand world they offer their own IP solution. So if you think that TCP/IP is not a good choice, then InfiniBand provides an alternative choice to you. But that's just mentioned, you need the IP specific cables and the IP specific adapter, and also the switch. So the switch would cost you like more than several $1,000s, which is not shown on the screen either. That you must use all these three things to interconnect your cluster. But then for the speed, it's quite good because it provides like 10 to 100 gigabit per second of speed, and then also it gives very low latency. But the bad thing is that the cost is really high. So given that you see that they do not use RJ45 cables, and then they need their own adapters, so some people start to think that using InfiniBand is somehow a vendor lock-in approach. So some people are thinking about high-speed Ethernet, which nowadays quite a lot of new customers are using high-speed Ethernet because they give a bit lower costs when compared with mainstream InfiniBand. But the bad thing is that when compared with InfiniBand, they give a bit higher latency. And then for the speed, often high-speed Ethernet is chasing behind InfiniBand. So when InfiniBand announce a high speed, then maybe several months or like a year later, then high-speed Ethernet will have the similar speed being announced. So somehow high-speed Ethernet is chasing behind InfiniBand, but the good thing is that they have much lower cost, and then people think that this is more vendor-neutral approach to use high-speed Ethernet to connect your customer. So after talking about interconnection, let's talk about storage. The storage part is I think, is the one of the easiest thing inside cluster, at least in a group of only several computers. So the two things is that you need to select your hardware, and then in your cluster you need to have a common storage space to store your files. So these two are the two hardware that you would choose, maybe SSD or maybe hard disk. So of course SSD provides higher speed, so we will use it as the main disk inside our cluster. But the bad thing is that SSD is much more costly, right? So and also the bad thing is that in SSD you use some NAND flash chips to store files. So in case the SSD got some problems, maybe you just cannot detect the disk inside your BIOS, or once you switch on, they just say they can't find the SSD. So in this case, when compared with hard disk, they have a lower chance of data recovery because it's harder to retrieve files from a electronic chip rather than the hard disk, which you still get a magnetic disk, right? And then for hard disk, although it is lower, but in terms of cost, it is much lower. So for hard disk, you mainly use it to backup files, and then also the good thing is that in case you need to do data recovery, you have higher chance to recover your files. And lastly, for the common storage is the storage space to use across your machines. And then in the sysadmin role is that we need to make it convenient for people to access. Because when you run things across different machines, you need to have a common storage that each machine can also access so that they can run the jobs on all the computers on your cluster simultaneously. Yes. And then, yeah, so for common storage, mainly you can use like the NFS, the network file system, and then you just mount a SSD or other hard disk on one of the machines on your cluster, and then you just export it to other computers on the same cluster. And then you can also do auto mount on your cluster so that when your cluster of computer is being started, they will mount that exported space automatically, so that when those other computers are start up, they would mount the space automatically, and then the users can just use it. And then this is one of the quite convenient approach to do common storage. So next will be co-processors. So in terms of co-processors in HPC, we mainly cover GPUs and also Intel Xeon Phi. So GPUs, there are quite a number of brands, or you can say vendors of the market. So the first one is NVIDIA, which supports CUDA and also OpenCL. OpenCL is the latest language announced by some of the tech hardware companies, which they would like to have a common language for people to write on, and then they could run the executable files being written using that language, and then they could be run on different kinds of hardware, such as GPUs, CPUs, or other kinds of hardware. So you can see that CUDA is being only supported on NVIDIA hardware, and then for AMD, it only supports OpenCL. And then, so what's the good thing about NVIDIA is that CUDA is being supported by many scientific computational software. So inside some supercomputers, you seldom see AMD GPUs, but rather you see NVIDIA GPUs if there exist any GPUs on the cluster. And then let's talk about Intel Xeon Phi. Intel Xeon Phi is something that you got 57 cores or more on it, and then you got a separate driver. So before that, you may see some news, I'm not sure, maybe on some tech site, you can see some news about Xeon Phi, but before, some people may imagine that once you install that card, and then inside the Windows Task Manager or inside Linux, you can just see 57 cores more, but this is not something true. So basically, it's actually a card being added onto your computer, and then what's the output is that you will have an extra space to SSH into, and then once you SSH into that space, you will see that's 57 cores extra. So as mentioned, you won't get 57 cores more just as normal CPUs. So you imagine this as a separate card that you can interact with. So, but what's good about Xeon Phi is that it can run x86 compatible software, which GPUs cannot. Right. So in case you haven't seen what Xeon Phi is, it's actually just a card like this, and then they got two versions. One is the one with active cooling, that means a fan inside the card, and then the other one is passive cooling, where you don't get a fan on the card, but instead you use the cooling solution provided on your server. So if you are only running workstations or running your own desktop PCs, you probably will really wants to use the one with active cooling, because the card really gets hot when it is running, or even in standby mode. So sometimes when I touch this metal here, so for the one without the fan, it gets really hot, like I think around like 90 degrees here. So it's quite dangerous, and then this card is quite problematic if you don't do active cooling enough. So if you have a passive cooling card here, and then if you do not do sufficient cooling, and then what happens is that the card will cut its electric supply, and then it will just pretend like you haven't installed the card on the computer. So it's quite problematic because restarting your computer can't solve the problem. You need to switch off the computer and then cut the power supply and then replug your power supply in order to have the card being workable again. But the good news is that your card won't become out of order for infinite period of time because it has some kind of self-protection mechanism. So let's have the versus on Xeon Phi and GPUs. So GPUs are more energy efficient in terms of flops per watt because on GPUs they got an architecture which is quite scalable, and also on each core it consumes much less energy. But then on GPUs you can't run x86 software, so Xeon Phi would be a solution if you like to run some x86 programs. Right, so it's time to mix all the things up into your cluster. So you need to make sure that different hardware, driver, software can all be installed onto the same machine. So this is the first step, and then the second step is that you need to make sure that there's no stability issues, because you really want your users to use your cluster instead of blaming the cluster is not working. So but sometimes we can really blame the hardware, because sometimes the vendor of the hardware just doesn't support any of these things that you mentioned, like the hardware or the driver or the software. So you really need to research on the information about your vendor and what kinds of software or hardware is being supported on your customer. Yeah. So last is about compilation and runtime. So quite a lot of people here have heard of GCC. So it's the GNU compiler collection, and it's free and open source. But in the HPC or in SIG SC, we mainly use the Intel compiler collection because it provides much stronger performance, and then you've got much more comprehensive collection of tools that you can use. But the bad thing is that Intel compiler costs quite a lot of money. So again, you need to pay quite a lot if you like to achieve better performance. Right. So MSVC, if you use Windows on your cluster, then you may consider MSVC. Otherwise, you can just ignore it. And for runtime, you need a message passing interface. So MPIs has to be used in order for your program to be run on your cluster of computer. Right. So last, let's talk about effective management. So your management has to be scalable. In some sense, that means you're not managing your own desktop or laptop computer. So your configuration cannot be doing it on a one-by-one basis, because it's ineffective and then also prone to human error. Imagine on one of the computer on your cluster that you type a wrong command, then that could cause some problems that you can't run your programs on that computer, or the whole cluster just got some runtime problems that you need time to debug. Right. So the common example is that you need to imagine you are running a national level computing center, which you can't configure servers one by one. Today you're working on server 1, and then the day after on server 2. So you can't do it in this way. You need to use some shell scripts to update all your servers in a single time. Right. So after talking about how students can participate in sysadmins in SIG SC or inside supercomputing, let's talk about how we can participate in supercomputing competitions. Right. So there are quite a lot of supercomputing competitions out there in the world. So the one with the longest history and then the most famous one is the SC, which I don't think they have a non-abbreviated name, because SC simply states supercomputing. So their brand is basically SC and then with the year behind. So in 2015 it's SC15, and then the second one would be ISC, which is also a very large HPC event. And then the last one will be ASC. ASC stands for the Asia Supercomputing. So this one is initiated in China, but in recent years it expanded to the Asia region, and then now the competition is open to worldwide. So in CVK we have been participating in ASC since 2013, and also in 2013 and 15 we are the finalist team. Right. So in 2013 been to Shanghai in China for the competition, and then in ASC 15 we have been in Taiyuan, China to participate in this competition. Both are in the final round. So ASC stands for ASC Student Supercomputer Challenge. It used to be called Asia Student Supercomputer Challenge because it was open to the Asia region, but then they would like to expand it to worldwide level, so they just changed Asia to ASC and then still calling the competition as ASC. So each year they got more than 100 preliminary teams and then around 16 finalist teams. So the constraint is that if you can't build IBM Blue Gene during the competition because they got a constraint that is you can only achieve the best performance using the power limit of 3000 volts. So your customer cannot exceed this power limit. If not, your performance or your result will be disqualified. So there are some challenges in ASC because unlike in SC, your server hardware, you can choose your server hardware yourself inside SC, and then there will be enough sponsor for you to get your hardware inside the final stage. But in ASC, the server hardware is provided by the sponsor, so you cannot choose it. And then you probably have not own the contest hardware, just like in SC, maybe you can choose, but in ASC you can't choose the server hardware unless you're so rich that you can get a contract with the sponsor that you can maybe buy some servers to test before the final round starts. And then there are quite some approach that you can spend nothing to just use this hardware being provided by a sponsor, or you can also spend some money to buy some best GPUs to accelerate the computation. But yeah, this costs money, and then this does not guarantee better results being achieved during the final round. And the last thing that is the most challenging, I think, is that you cannot switch off anything, or you cannot, replace any hardware during the final round of competition, unless there are some faulty parts that you can change, unless you cannot switch off any server. Right. So let's cover some context questions. Maybe some of you, I'm not sure any one of you here know about this question. So in some supercomputing competitions, I think the first question is the most common. It is about LinPack or HPL, which basically tests the performance of your cluster. So HPL, it stands for High Performance LinPack. And the second one would be HPCC, which is less famous because HPCC is a bunch of benchmark that will be run. So in HPCC, HPL is part of the HPCC benchmark, but there are much more software to be run, so it could be much more challenging. So depending on the number of participants, maybe sometimes the organizer of the competition would like to use HPCC to challenge the contestants, but if they do not have enough contestants, they probably want to use HPL instead. So other than those only doing benchmark things, so we also got some more real-world related things like the NAMED, which is actually simulating some large biomolecular systems. So maybe sometimes it's about some proteins, or sometimes it's about other things, but mostly I think it's about protein. So in the real world, we also do some weather forecasting in some good laboratories or observatory. They give very accurate weather forecast result. That's because of their use of supercomputer. So we call it ROF, or a weather research and forecasting model. So we also run this kind of software on our cluster during the competition. And then we also got other things like the LBN as the boss thing inside our competition, and also got the gridding thing. So the gridding thing is actually the Square Kilometre Array project, which is I think the base is in Australia. So what we do is actually trying to optimize the performance of our program, which is being supplied by the SKA project. So that what we need to do is to optimize the code to give much better results. So that I think the SKA project will eventually get our code, and then so that they can achieve better results when they do their data processing. And then the last thing is something quite new, is actually the high performance conjugate gradient. And then because why this HPCG project is being developed is because nowadays in HPL, so some people in the HPC field thinks that okay, so nowadays you guys are raising the performance of HPL, but they think that HPL is not a good indicator of your performance of the cluster. So they developed something called HPCG, which is much harder to optimize, and then they really think that HPCG is the real indicator of your performance of the cluster. So that's why HPCG is being developed. So yeah, so text could be boring, so let me bring some pictures. So in NAMD, we basically are doing some computations on some just some molecules, and then so it could take some time, and then based on the complexity, you need like several minutes to several hours of time to compute the final optimal result of that molecule. And then, so as we mentioned, we need to use GPUs. So of course that's not about using one GPUs or using your home grade GPUs. So all we brought to the final condition was like 9 GPUs, I think, but it was quite sad that we didn't use any of them during the final condition, because after some evaluations that we think that we just think that this is not a good approach to use GPUs, because we think that there are some reasons which I will also cover later. But using GPUs is really not a cheap approach, because each of them cost like $8,000, and then then we didn't use any of them. And the other thing is that we are still using the domestic grade GPUs. So some of the winning teams or the really strong teams, they use some industrial grade. I would say industrial grade, but maybe data center grade. So their GPUs are costing like $20,000 each. So they got much stronger GPUs than ours, but due to our project concerns, we only bought some domestic GPUs. So what's the use of GPUs inside SC? So it's actually about some projects being giving out some GPU code for you to run, and then maybe they are HPL and then the protein folding thing like the NAMD, or there are also some weather forecast software that would provide GPU code for you to run on GPUs. And depending on the workload, the optimal number of GPUs could vary, because it's not about all the time that you use the maximum amount of GPUs that would give you the best result. Because if you use the most amount of GPUs, maybe they could not give you the optimal result. Sometimes maybe 3 GPUs is good enough, but sometimes maybe the more the better. So that depends. And then the last thing is that double precision computation is much slower than single precision computation. Because on some GPUs, due to some power usage concern, they would like to use single precision, and then so that's something about precision or performance selection when we use GPUs. And then in CPUs, most of the time we compute DP, so that's double precision. But then in GPUs, you can choose whether or not to use SP or DP. But then SP is much faster. DP could reduce quite an amount of your performance. So that's also one of the constraints that you need to think about. And then there's a dilemma of using GPUs. So actually, it's placing a bet on the type of context questions, because some context questions announced they may not have some GPU code. So if you install the GPU on your cluster, then you just cannot take it back after the final round starts. But then before the final round starts, you don't know the final round questions. And then for GPUs, you need significant amount of power to run, and then even they are in idling stage, you still need to spend some power on those idling GPUs. So you're basically sacrificing the amount of CPU cores to feed some idling GPUs in this case. So you really need to think about this GPU programming skills of your team. If you think your team is strong, then you may deploy some GPUs. If not, then sticking to CPU is more safe because CPU is more generic to run scientific software. And then, just as mentioned, participating in SC is actually quite resource intensive because quality participation in SC, you need significant amount of resources. Money is the first concern, and then you need technologies backing your training or your courses. And then you also need technical and administrative support because, of course, when we deploy our cluster inside CRHK, we need technical support to provide networking. And then also we need some administrative support so that we can communicate with the organizer and also do all the logistics before we can go to the final round of the competition. And then recently, we also heard in the news that in South Korea, some college students are being trained with supercomputing skills, which is actually quite good news because in South Korea, they got really quite a lot of resources so that even some college students, they can also participate in the supercomputing field, which previously is quite, restricted to those national graded computing centers. And then, so this is almost the end of my talk today. So then I'm not sure whether some people here, got any Linux distro installed on your computer. But one way to experiment with Linux distro is that you can install it inside a VM, or also you can also test some online VPS or cloud providers because that would be the most the easiest way for you to deploy Linux and for you to test. And the reason why I put up this slide is because I used to give some similar talks for the SIG SC training, and then so I like to give people the easiest way to train themselves on Linux instead of getting time being spent on something that they cannot train their Linux skills. And yeah, so I think that's the end of my talk. And then yeah, I know today's talk could be a bit boring because in the previous session you got some hands-on on some really fabulous frameworks or some web programming things. So today's talk could be a bit boring, but I hope you guys got to know about something in supercomputing today. And thank you.
Thank you, Evan, for giving us a very interesting talk. It's not boring actually, I quite enjoy it. So if you guys have anything to discuss or question, you can raise it now. Any question to Elton? So if there is no any question, and we can move on to the next room, and we have some drinks and free drinks and snacks, and we can discuss with Elton or each other in next room.